system that operates the MEMS sensors to detect Earth. So we use the Samsung Galaxy S7 as a seismic sensor. SK Telecom provided this smartphone, so it's a brief specification of sensors. So we first used 300 smartphones as a seismic sensor. And then installed these these smartphones at the SK Telecom base stations. So the last two large earthquakes occurred in this area. Also, my university is located in this area. So we installed these 300 sensors nearby my university and then this area. So as you can see, we put the smartphone on the floor at the base station, and then the device smartphone is connected to one power. So we don't need to worry about the power consumption or energy efficiency of the smartphone application. And then we needed to measure or assess the quality of MEMS sensors to use them as a seismic sensor. So we assessed the quality of the MEMS sensors in terms of sampling rate and noise analysis. So the smartphone continuously sends the data at 100 Hz rate, and then as you can see, their distribution is quite rigorous. And then we analyze the smartphone's noise. So to analyze the noise of the smartphone or the sensor, we use several tools such as FFP and PSP and PDM. So as you can see, even though we use the same hardware as a seismic sensor, they have the different noise patterns. Like there are some periodic noise coming from the heating or the air conditioning or the other server systems, and then there are continuous noise the other sources. And then it is quite good example. So to analyze the source of noise and then the kind of noise characteristics, we also use various calculations. So as you can see, we classified our devices into three groups. So this is average sensors that can be used as a seismic sensor, and then this is the worst sensor that should be excluded from our seismic vector. And then this is best sensor, only 5 to 10% have this quality data. And then we also analyze the noise using the calculation to figure out the types of noises. So as I explained already, there are some periodic noise coming from the outside environment, and then the sensor itself has noise because the type was issue. So we analyze the noise types using the discrete variance, and then after this thorough evaluation and assessment, we determine that our sensors, sensor-based seismic network can detect or spec of both 3.5 or 3.0. And then based on our analysis and evaluation, we constructed DAy system using the MEMS sensor and DAy2 network. So I briefly introduce our system. So this is the system overview. So as you can see, we collect the accelerometer data from the sensors. They continuously send the accelerometer data to our server. And the gateway layer, it collects the data and classify them into different levels of quality. And then we use the deep learning algorithm to detect earthquake. And then there are several message queue and server and analysis server or the database to archive the data. And then we also have the visualization server so that the administrator can easily monitor the system. So this is the current monitoring system. So as you can see, in the map, you can see the installed sensors, and then we provide some statistics such as the system content resource statistics or accelerometer statistics or the number of sensors. So the administrator or the programmer can easily find out, figure out the problem or the state of the current system. And then one important feature of our system is to detect abnormal sensors because we cannot control the base station, so there are many different events or the noises. So there are normal sensors and abnormal sensors. So we needed to explore this data about the sensors from the sensor network. So we developed the anomalous algorithm, and then we excluded those anomalous sensors. As you can see, green are good sensors, so they can be used as a sensor. And the orange and red sensors are disconnected sensor or the sensor that can poor color. And then we use the two types of artificial algorithm. First, we use the ANN, artificial neural network, exactly the same model of the eye shape, but different data set. We use the Japan data set and the US data set. And then to improve our model, because our sensors, smartphones, are always connected to one tower, so we don't need to worry about the system, worry about the power consumption. Also, we have a powerful server, so we send all the data to the server. So we decided to use a new model using the deep learning technique. So this deep learning technique model has a combination of CNN and RNN. So after my talk, Dr. Lee will present more details. So this is the details about this work. Then, so after we installed the sensors and the system, our system detected 3 earthquakes. The first one occurred in 2019, February 10th. The magnitude is 4.1. So as you can see, these are the sensors and these are the wave recorded smartphone. Also, our smartphone and the sensors were smaller earthquake. The right one was the magnitude 2.9, and then left one is magnitude 4.1, but it's far from the station, more than 50 kilometers. So we successfully detected these 3 earthquakes. And then, as a future work and for the ongoing work, we will increase the number of the stations, and combine the traditional sensor network and this mesh sensor-based network. So as you can see, these are current sensor network, and then we will add more sensor network using the mesh sensors. They will be installed at the station. So SK Telecom developed the earthquake monitoring device like this. So it has very simple hardware. So it consists of the 3-axis accelerometer and SD modem, 4G modem to send the data to the server, and it has very small battery in case of power outage. So this is the figures of our system, our device. So as a future work, we will combine the traditional scientific network and sensor-based network. There are several research issues, topics, and then from the next month, we will work. I will work with the UC company, with Richard Eller, for in terms of triggering algorithm and data archiving, etc. So as a conclusion, sensor-based sensor network can be used to help the traditional sensing network in computer performance. Okay, so this is my talk, and I can take the question.
Are there any questions?
So also I have a poster over there. So if you have any other questions, so please approach me, my graduate student, and I can answer to the question.
Great. Okay, let's move on then to the adjoining talk by Dr. Lee about the deep learning using networks.
Good morning, everyone. My name is Tolo Lee. I am from the Florida Institute of Technology, and this is a joint work with Xin Wang and Jiangsu Li and Professor Guan. And I'm going to present our work on deep learning for the earthquake detection using low-cost land sensors. And this research was conducted by KMA. And as Dr. Guan explained, local sensors has been actively used for monitoring and detecting earthquakes. For example, the quake catcher network, community seismic network, the PLN network, and the MyShape. Among others, the MyShape is the most recent and successful effort on developing the earthquake early warning system based on the local sensors. As Dr. Allen gave a presentation, MyShape is using the participatory smartphones as the seismic sensors in a crowdsourced manner. And as you can see here, as he explained, the main algorithm they adopt is a machine learning algorithm, which is artificial neural net model. And this is running on its smartphone to detect earthquakes. However, although it's great success, it has two limitations. The one is the heterogeneity across different smartphones can negatively affect the detection performance. And the second one is any model may be an energy efficient solution, but may not be optimal for detection performance. This is a good compromise between for the trade-off between the power consumption and performance. On the other hand, the advances in deep learning and data mining have motivated several recent studies in seismology. For example, the searching for the repeating seismic signals, identifying the previously unidentified earthquakes, and the phase peaking. However, deep learning techniques have not been actively explored for the real-time earthquake detection. So in this work, we'd like to answer a question. How far we can go by leveraging deep learning for real-time earthquake detection when the energy efficiency is not of the primary concern, and also the well-managed sensors are used. In this work, the contribution is we present a convolutional recurrent neural net model that achieved a 99 detection performance with the first alarm rate that is less than 1%. It has also been able to detect a few small earthquakes in practice. And this is a key component of our newly built network system of the local sensors, as Dr. Guan explained before. And this is a map of the smartphones, basically, that are deployed on the southern area of the South Korea. And basically, we're using the built-in local sensors. And the distinction point is that we use fully power supplied smartphones. So we don't need to worry about the power consumption. And also the sensors can directly transmit the acceleration data to the backend solver, which is a gateway. And as you can see that we have the 3-component acceleration data. And this will be fitted into the deep learning model that I proposed in this work. And this will classify the activity. The way we formulate the problem is a binary classification problem. So either earthquake or the non-earthquake. And then the result will be delivered to the data solver along with the raw data. And the raw data will be used to locate the abnormal sensors, if any. And also, all the results will be delivered to the monitoring solver for the visualization. In the event of earthquake, the entire system can detect the earthquake and give the early warning signal. And this is a deep learning workflow, and I'm gonna use this workflow to explain about our model. First, I will explain about how we collect the data and process, and then explain about our model in detail, and then talk about how we train the model and the results. Since we model the problem as a binary classification, so we need to have the two different classes of data. The first one is earthquake data. For the earthquake data, we use about the 2000 Japan earthquake records, whose largest PGA value is greater than 0.1Z. For non-earthquake data, we use the background noise in several different environments and also various human activity acceleration records. The reason to use the second bullet point is that we'd like to emulate possible non-earthquake records that are captured by the smartphones. Here's the data set. Here is the data unit. And we are using the 2-second sliding window with the 1-second overlap, which is exactly the same as the used in the MyShape. As you can see here, this is about the 10-second acceleration data at the 3 components. And basically, you can see that this red box indicates the 2-second window, and this slides over time. And this is the current window, which is overlapped with the previous window over the 1 second. Let's wait. And then the next question is, how we need to select the time period of earthquake waveform for the earthquake samples. As you can see here, the first portion of the earthquake waveform may not be the result of the earthquake, so we have to exclude this portion. And also the ending part may not be the significant component of the earthquake waveform. So it is critical how we select the time duration of the earthquake waveform. In this work, we first consider 2-second duration around the peak value, the 1 second before and the 1 second after. And the second is, we use a 4-second window. That's 4-second duration, which is the 1 second before the peak and the 3 seconds after. And 10-second duration, that's the 1 second before the peak and the 9 seconds after. And another aspect is a sampling. As you can see here, this signal is a continuous signal. However, we cannot store continuous signal on the smartphone. It is impossible. So when you look at the 2-second window, you can see that we can see the continuous signal, but the data point is this kind of the sequence of the data points we have to store in the smartphone. So now the question is, how many data samples, how many data points we can store in the smartphone without losing any accuracy? So we notice that we can use the sampling rate up to 100 hertz. That means we can store the 100 data points per second without having any variation on the time interval between the consecutive data points. So we can, even if there is some variation, we can safely ignore it. In this work, we consider the 100 sampling rate and also the 50 hertz and the 25 hertz for comparison. And this is a summary of the data samples for the model training and testing. As you can see here, when you increase the selective duration for the earthquake samples, we can increase the number of the earthquake samples. Although non-earthquake samples are pretty much the same. And this is the model that we propose in this work. And this is a combination of the convolutional neural net and the recurrent neural net. Here, distinction point is that we use 2-second sliding windows directly as the input samples instead of using the handcrafted features or the spectrogram of the long time period waveform that have been popular in the literature. And the second point is we utilize a convolutional neural net part to automate the feature engineering to extract the informative features after filtering out the noise. That means that we don't need to have the pre-processing of the data to extract the features to be added into the model. And the last part is the recurrent neural net part, and this is to introduce a notion of the memory to the network to capture the time dependency within and across the time samples, the data samples. The reason is that the earthquake data has a time correlation, obviously. However, the previous approach ignored that kind of time dependency across the data. And the next part is to train model. And here the main point is how we can deal with the data imbalance. And previously, the only work used downsampling or the oversampling. Instead of using that, we use the weighted loss function so that we can make a balance. Instead of decreasing the number of the samples or the boosting up the number of samples, we use the number of samples as is. However, we change the weight values for earthquake samples and the non-earthquake samples. For example, we have less number of samples in the earthquake, so we increase the weight values for the earthquake samples, and we lower down the weight for the non-earthquake samples. All right, here is the results for our model, and as you can see here, perhaps if you don't have any background in machine learning, and I'm going to tell you about how we can interpret these results. And here, the blue line should be close to the upper right corner, and the PR curve, this should be close to the upper right corner. This means we don't have any false alarms. And this is the pretty much ideal case, and this indicates that we can achieve the 99 detection performance with the false alarm rate less than 1%. And for comparison, we're going to bring up the ANA model that's used in MyShape. As you can see here, and the blue lines are not very close to the upper left corner or the upper right corner. And we noticed that the ANA model is quite sensitive to the settling rate and also the how much the time duration we choose for the earthquake samples. And also there is one caveat. This is the model that we trained separately and independently from the UC Berkeley group. So the parameters of the model may be different from what they are using, and also perhaps they enhance the model in the current version. So there may be some difference between what we use and what they are actually using. So yeah, so you need to take this result with some sort of. This is the computational cost, and because the deep learning has been considered as a computationally very expensive solution, so someone may raise a question that this may not be suitable for the real-time operation. But we noticed that with the 300 sensor data, the runtime of executing our model for each 2-second input sample takes only about 49 milliseconds for CPU and 22 milliseconds for GPU. And how you can interpret this one is that here the table is, we increase the number of sensors, and the first one is when we use the CPU, and the second one is when we use the GPU. As you can see that, and the 300 sensors case is what we are actually using right now, and we have a plan to expand this network to the 8,000 sensors. So we would like to see the feasibility of this model, and you can see that the runtime of running this model is still less than 1 second, and you can see that this is still about the 800 millisecond when you use the CPU. When you use the GPU, we can drop it down to half of that. Okay? So it means that it is scalable to thousands of sensors. And here's a case study, and this is our earthquake that happens on February 10th this year. It was a magnitude 4.1. And you need to look at the second bullet point here, and the largest PGA was 0.0045 G. And as I mentioned, we are using the Japan earthquake data, whose largest PGA was 0.1 G. And actually, we are using the large portion of the waveform, so we were able to detect this kind of small earthquake signals. You can see that this is the acceleration record that we obtained from the smartphone. You can see that this noise is hardly distinguishable from the waveform that we can obtain from the earthquake. So here's the results when we use an ANA model and the pretty much random. This means that this doesn't work properly. However, when you apply our CRNN model, and you can see that this one is able to just pick up the earthquake waveform properly in the presence of the background noise. And here are the other sensors results. And you can see that our model is able to pick up the RSK waveform properly. Right, here is a conclusion. We have proposed a convolutional recurrent neural net model that shows remarkable performance for the real-time RSK detection using the local sensors. And we have identified that the computational cost is not that significant, it's still manageable. And also our model has been able to detect the small RSKs in practice. Thank you. I'd like to tell you one thing. I'm also from the computer science, so I was very nervous at the beginning of this talk, so please understand it.
All right,
Is there
thank
any
you.
question? Yeah.
It's great welcome to you, deep learning for seismology, and I say your loss function. And if there is I see the loss function, there is no loss for the time. I mean, if there is a seismology, it lasts for 30 seconds. And actually, for your target, you want to as fast as you can to determine this is a earthquake. But you may from this loss function you couldn't know if your network tell you at 6 seconds or 10 seconds tell you this is an earthquake, you couldn't say the difference between them. Is it correct?
So actually, the loss function in the machine learning has nothing to do with the data delay. It is all about when we have an input example or the sample. Let's say we have the 2-second window. So what I'm going to do is that this model is to classify that is an earthquake or not. And in order to build such a model, we need to have the loss function. The machine learning model is all about just building a model to solve the optimization problem. So we use this loss function as objective function to minimize. And that way we can build our model. In other words, we can optimize the parameters of the model. Here we have the bunch of the layers, right? And each line is associated with the weight value, but we don't know what kind of weight value we need to use. So in order to obtain the values of the weight, we have to minimize this loss function. So
Yes, I understand. For the deep learning, the monthly or deep learning, the deep learning, the network is done, the weights, extract the parameter by itself. And then the loss function is to judge the weight is training correct. So
right. So here what you can see is that let's say the input signal is a result of the RSK and the output is not that, then we penalize the result. And the same thing happens for the opposite case. So we like to minimize such a misclassification. That's the goal of this process. Now just how we can deal with the delay. Let's say the input samples are delayed, and in my opinion, it has nothing to do with the deep learning model. Yeah.
So you showed that you were really focusing on detecting the peak shaking. What?
Yeah, right.
So you're focused on detecting the peak shaking. Why not detect the P wave arrival? That gives you much more warning time.
Right. Right now, our focus was on picking the S wave. That's the way we train the model. But as you have noticed that our local sensors is capable of picking up the P wave as well. But we were concerned about picking up the P wave. So we wanted to clear up the only question regarding whether we can just pick up the S wave first, and then our plan is to lower down the threshold and then just pick up the P wave as well. If the P wave magnitude is greater than the S wave, obviously we can detect that, but normally that's smaller than swing. So our plan is to move on detecting P wave as well.
All right, maybe we can continue the discussion during the break, which is right now. Thank you very
Thank
much for this morning's speakers. And we'll meet back here at 11 o'clock.